Hello, I'm Brian Dunn, and this is my simple harmonic motion lab report. So my group analyzed simple harmonic motion in relation to extreme sports, specifically bungee jumping. To represent bungee jumping, we used a system consisting of a hanging mass, a spring, and a pendulum mount. Our objective was to examine the motion of a mass spring system in which the mass swings in an arc while oscillating on the spring, to determine the fundamental principles that govern the motion of this system. Our model works both to evaluate the motion of a pendulum and a mass spring system. The horizontal motion of our model will determine the pendulum aspect, and the vertical motion determines the mass spring aspect. Our results found that the data was consistent with the laws concerning simple harmonic motion. Before starting the experiment, we wanted to find out some of the basic physics principles that define simple harmonic motion. We know from Newton's second law that force equals mass times acceleration, and we know from Hooke's law that force equals negative kx, where k is a spring constant and x is the displacement from equilibrium. Setting those equations equal to each other shows that mass times acceleration equals negative k times x. And we know that acceleration is the time derivative of velocity and the second time derivative of displacement. Substituting that into the above equation shows that the second time derivative of displacement equals negative k divided by m times x. We also know that omega equals the square root of k over m, so we can rewrite that equation as the second time derivative of displacement equals negative omega squared times x, which is the differential equation for simple harmonic motion. The solution to this differential equation is a sinusoidal function, either x of t equals a cosine omega t or x of t equals a sine omega t, where a is the amplitude and omega is the angular frequency. To carry out our experiment, we used a hanging mass of 250 grams, a spring, a pendulum mount and ring stand, a video camera, and the tracker software. So first we hung the mass from the spring, which we attached to the pendulum mount. As shown above, we displaced the spring down and at an angle to initiate horizontal and vertical displacement. Then we released the mass and filmed its motion for about 12 to 14 oscillations so that we had plenty to choose from in Tracker. So then we imported the video into Tracker to obtain position versus time graphs for both the horizontal and vertical motion of the mass. Here's a video of Tracker recording the motion of our system. After I set up a coordinate system based on where the spring is attached to the pendulum mount and selected a time interval for which to record, Tracker recorded the x and y position of the center of mass of the object and then created appropriate position versus time graphs as seen on the right. I talked earlier about the possible equations for simple harmonic motion. I needed Tracker to adapt these equations to my particular model. I used Tracker to find amplitude, omega, and whether it was a cosine or sine function. Since omega is something I can't measure directly from the graph, I used the equation omega equals 2 pi over period. Period is something I can measure directly on the graph. This is Tracker's Analyze feature, which shows the graphs of x and y position versus time. Parts of the graph are sloppy, so I needed to find a consistent set of data, which for x is here and for y is here. The first thing I needed was amplitude, which is the distance from equilibrium. So I found the y value here, the y value here, subtracted the two, and divided by 2 to find that distance from equilibrium, and I did that for both graphs. Next, I wanted to find period because I needed to find omega. Period is the time it takes for one oscillation, so I found the t value here and the t value here, and then subtracted them to get the period. Once again, I did this for both graphs. The final thing I needed was to figure out whether it was a sine or cosine function. Since both of these start at extremes and not at equilibrium, I know that they are both cosine functions. After finding my values from Tracker, I began plugging into my equation. I found omega by simply doing 2 pi over t, t being period, and then plugged in amplitude and omega to get x of t equals 0.035 cosine 5.108 t, and y of t equals 0.025 cosine 10.471 t. To determine whether or not our system follows simple harmonic motion, I decided to compare the t values that I measured in Tracker to the actual t values according to the fundamental simple harmonic motion laws. We know that the period of a spring is 2 pi times the square root of m over k, m being mass of the spring and k being the spring constant. The period of a pendulum is 2 pi times the square root of L over g, L being the length of the pendulum and g being the acceleration due to gravity. And for our measurements, mass was 0.25 kilograms, spring constant was 30 Newton meters, length of the pendulum was 0.375 meters, and acceleration due to gravity is 9.81 meters per second squared. After plugging my experimental values into the formulas for period of the spring and period of a pendulum, I found that the expected period in the x direction was 1.228 seconds, and the expected period in the y direction is 0.573 seconds. Calculating the percent error, I found that my measured period was 0.125% off in the x direction and 4.607% off in the y direction. Possible sources for this error include errors in the center of mass placement in Tracker, and also my errors in selecting where the period and amplitude begin and end. My equations support that the model we created does in fact abide by simple harmonic motion. The graphs in Tracker were both clearly sinusoidal functions, and the measured period values were very close to the expected values, close enough to assume any error to be due to measurement. The x equation can be seen as the motion of a pendulum, as the horizontal motion of the mass reflects a mass swinging on the end of a pendulum. Therefore, the x equation takes into account the period of a pendulum. The y equation can then be seen as the motion of a spring, as the vertical motion of the mass reflects a mass oscillating on a spring, and the y equation takes into account the period of a spring. Comparing the two periods directly, they are different, as the period in the x direction is double the period in the y direction. Since the period of a pendulum relies on the length and gravity, and the period of a spring relies on the mass and spring constant, it makes sense that these periods are not equal. This concludes my simple harmonic motion lab. Thank you for reviewing my submission.